Okay, so good evening to all. My name is Shobik Dey and welcome to this seventh live session. Today we will be discussing the assignment number 7 and I will be sharing my screen. Sorry for any kind of background noise that you could be hearing because of the Ganpati Visarjan. Okay. I hope my screen is visible. So we will be discussing assignment number 7 today, and it's a continuation of the load study problem, and we will be looking at the various kind of methodologies for finding out the bus voltage, then your power and all, using this Gauss-Seidel or Newton-Raphson method. And as said earlier, we will be taking a look at some of the specific, unique problems of every assignment, and it is also the same with this assignment also. So, just one minute. Yeah. So let's start. So we'll be first discussing question number 5. Now this is the diagram concerned with the question. I hope the diagram is clearly visible. Anyways, I will be sharing this file also with you. So let's start. The problem says that the figure shown above shows the one-line diagram of a simple power system with generators at bus 1 and 3. The voltage magnitude of bus 1 is adjusted to 1.035 per unit, and the bus voltage magnitude at bus 3 is fixed at 1.015 per unit with real power generations of 100 megawatt. Mind you, these are all generators. Okay, so good evening. We were discussing the some of the typical problems of assignment number 7, and we will be starting with this figure problem number 5. So they have shown this single line diagram over here, and the question states that the figure shows above the one line diagram of a simple power system with generators at bus 1 and 3. So this is a generator, this is a generator, and the voltage magnitude of bus 1 is 1.035 per unit, and the magnitude of this is your 1.015. Mind you, just note the difference. So this is a slack bus. As you know, what is a slack bus, I did not say. So these are reference buses for calculating the power losses, and generally we consider one of the PV bus as a slack bus. And this bus number 3, here you will see that it is at an angle of 0, right? This V1. However, this V3, it is not at an angle of 0. So it must be having some other angles. We will see later, but you will see that the magnitude of it is 1.015 per unit. This is a very important observation because your question number 5, 6, and 7, all of these are connected. Therefore, noting this difference is very important since both of these are generated buses 1 and 3. Okay. Now going to the next statement. So a load consisting of 400 megawatt and 150 megawatt is taken from this bus number 2. And a load of 250 megawatt is taken from bus number 3 itself. As you can see in the diagram, everything is clearly written, and they have told the base MVA to be considered is 100 MVA, right? Now, using the Gauss-Seidel method, they have told us to find out the bus voltage magnitude at bus number 2 after first iteration. So first, only first iteration. And they have also told, so this is very important, assume this flat start for the load flow. Okay. Yeah. So now the very so the starting methodology for this kind of problems is you first construct the admittance matrix. So in the previous week we did see what is our admittance matrix, we did draw some also, so I hope the concept is clear. Now all of these parameters from line 1 to 2, then line 1 to 3 and 2 to 3, all of these are your impedances. Now we have to construct the admittance. So y12, that is between 1 and 2, bus 1 and 2 is 1 by z 1 by 2, which is your 1 by this 0.02 plus j 0.1, and it comes out to be 9.806 minus 78.69 degrees. So when I convert this into complex number, it comes out to be this value. So similarly, you do this for y1 and 3 and y2 to 3, that is between bus 1 and 3 and bus 2 to 3. Okay. Now we have all of these parameters. Now we can construct the y bus I mean admittance matrix. So capital Y12, which is equal to capital Y21, it is equal to minus Y12. We have the value, and again here same goes for this also, Y13, which is equal to Y31, it is equal to minus Y13, and your Y23, it is equal to Y32, and it is minus Y32, small y32. So your y, capital Y11, which is the sum of the admittance of the total number of transmission lines that are connected to bus 1, which is Y12 and Y13. Similarly, you get Y22 and you get Y33. Now, so this is just for your reference. So if you look at the question, they have told us to determine your what is the bus voltage at the bus number 2 after first iteration. So you need not calculate y11 and y33. Anyways, I mean, you may need all of this information for your later problems that are coming up. So now this is a very important thing. So all of these informations I have given. So base MVA is 100 MVA. Your V1, the magnitude is 1.035 per unit. Your P1, which is 1 per unit, and this, so okay, so v3 is 1 point, anyways we need not need this information right now, but so v3 is 1.015 per unit and v2 is 1 per unit. Now this is a very important assumption. So now when they tell you that assume flat assumptions for the load flow, start for the load flow, flat start for the load flow, and you have not been given the information of what is the voltage given the information of what is the voltage at your any kind of bus, so you can assume that the voltage at that corresponding bus. So we have not been given the voltage, what is the voltage at bus 2, and when they have told assume flat start for the load flow, you can take it to be 1 per unit. Okay, so this you can take. Now we have to calculate what is the apparent power at your bus number 2 in per units. Now just look at the diagram. So bus 1 and 3 are generating bus, right? And bus 2 is a load bus. So your any kind of so for a generating bus, we take the apparent power to be positive. So the real power as well as the your reactive power are positive, and since the load bus is consuming the load, so that is taken to be negative. So that is why I have subtracted it from 0, and that is why I have introduced a minus here. So basically due to consumption, and this is divided by the base MVA, which is 100. So when you do this, it comes out to be minus 4 minus j 1.5. And also it is told that your, if you see this diagram, um, the generated bus 3, it is generating 100 megawatt, but the bus is consuming 250 megawatt. Therefore, your power would be the total, the net power, which is 100, the generating minus the load, which is being consumed, which is minus 150 by 100, which is minus 1.5 per unit. So, having calculated all of this, you now have to calculate what is the bus voltage at 2. What is the voltage at bus 2 after first iteration. So this is the formula for this, where here, so this is P2 minus JQ2. We already just calculated this. So H2, which is, this is your P and this is your Q, and this is V20. So V20 basically means your starting, what is the starting bus voltage. So zero basically means at zeroth iteration. I mean just at the starting. So that is why I've written this zero. And this is asterisk, which means it is just the conjugate of it. Provided there is a complex term, you have to take the negative of it. I mean you have to take the opposite sign of it. If it is plus j, you have to take minus j, and vice versa. Since we don't have any complex term here, we can directly write 1. Okay. So now and also, okay, so you just place it. Be very careful about the sign. So this is P2 minus JQ2, and H2 is P2 plus JQ2. So this J minus minus becomes plus, so this becomes minus 4 plus J 0.5. Be very careful while solving the, I mean solving this kind of problems, because this is highly calculation intensive, and also be very careful about the sign. One mistake you do, it will lead to a wrong answer, and it will be a total wastage of time. Okay. Now minus 4 plus j 1.5 into sorry plus, now it comes your v1 minus y21 into v1. Now why I have written this plus, it is very simple. So you saw that y121 or y21, whatever you may consider, it is equal to minus y12. So and your y12 is this. Now when you replace this, so I mean y12 would be capital Y12 would be Y21, sorry, capital Y12 would be small plus small Y21 into V1. So that is why this plus sign comes. Similarly for capital Y23 also, and this is 0 as I told. So here V3 also, we have to start with the initial values, and we have to go in order, right? 2, 3, 4 in this way. So that is why this 0 is there. And we also know this value. So V1 is 1.035 and V3 is also 1.015. Now when you, now you can see how lengthy this calculation could be. So you have to be really very attentive and focused while calculating this kind of, I mean performing this kind of calculations. Any mistake you do, you may not get the right answer. So I mean finally when I do this, it comes out to be 0.916 at an angle of minus 15.78 degrees, which is your option A. Now we have to stop here only, because clearly they have told us that what is the voltage at bus 2 after first iteration. So after first iteration, that is why this is written as 1. Your this will be and they have told us to find out the magnitude. So this would be 0.916, which is your option number, your A. Now, for example, suppose if they had told you to find out what is the bus voltage after second iteration, now this would be a really very lengthy problem. For that case, you have to also find what is the bus voltage at V3 after first iteration, because in the second iteration, your this would be V2. Your superscript will also be 2. Now, when you will be calculating this, you would require what is the bus voltage at bus 3 after first iteration. So this would be Y23 at an and your superscript would be 1. This V1, we won't be, I mean we won't do anything with it, because V1 is, as you can see in the diagram, it has been considered as a slack bus. So we don't need to do anything. It is as per the convention. Okay. So this is how you get as the answer is 0.916, which is your option number A. I hope I was able to make this clear. Anyways, you will be getting the access to these materials, and also I'll be posting the video, you can watch it. Now if you don't have any questions, I'll go to the next problem, which is so question number 5, 6 and 7. We will be looking at this all together because these are connected. I mean, same problems but different questions. So again, question number 6, so again the same figure. Here they have told, so using Gauss-Seidel method, find out what is the bus voltage. Hello. Hello. Surya, are you saying something? Okay. Now they are telling ki using the Gauss-Seidel method, find the bus voltage angle at bus number 3 after first iteration. Again, assume flat start for the load flow. So I have again here written what is the I mean, using Gauss-Seidel method, how can you find out the bus voltage after the first iteration for bus number 3. So it is the same formula for bus 2, bus 3 as well. Here, so you can see that here there is P3 minus JQ3, right? Now if you look at the problem, they did mention that a load consisting of 400 megawatt and 150 megavar taken from bus 2, but they haven't specified what is the reactive power being consumed or being produced from bus 3, right? So they have only told that a load consisting of 250 megawatt is taken from bus 3 and it is also generating 100 megawatt. So your net what to say, this active power from bus 3 in per unit will be 100 minus 250 by 100, which is your minus 1.5. So we need this Q3 also, right? Because clearly this is a generator and it will be generating some reactive power. So we need to get a hold of what is Q3 for processing, I mean, for calculating V3 after first iteration. So the formula to calculate your Q3 is this. So this IM is your imaginary, right? IM, because this is a complex number, and you know that in VAR, right? Reactive power, I mean, in apparent power, it is always active power plus J. I'm plus J into your reactive power. So that is why that J term. So it is an imaginary term, right? So that is why this IM is there, because you only have to take into account what is the magnitude related to the J term. So that is why this IM is there. And this is V3 star with 0. Again, this is the formula. So since you are calculating after first iteration for V3, and this is in, I mean, what to say, in arranging order, so 1, 2 and 3, so that is why you have to take V2 after first iteration. So that is why that previous V2 wala information is required here. So now again, since this is a V3, we have the magnitude here 1.015. We don't need to care about any plus J or that, like that. So that is why I have just written 1.015. And when you do this, be very careful, right? Because there will be plenty of real term and plenty of reactive this complex term, J term. So after calculating this, I only extract the term which is J, the term which is connected with J. And that is why I had written this imaginary, to extract only that term. And it comes out to be your 0.3086. Therefore, your reactive total apparent power at bus 3 would be minus 1.5 plus J 0.3086. Hence, you can easily see that bus 3, it is consuming 1.5 per unit real power, and it is generating this much amount of reactive power. It is clear from the symbol. So again, you put all the terms and, I mean, values are known, and you put this in this equation, you get what is the voltage after first iteration at bus 3, which is your 0.9557 minus J 0.158. Now here there is a funda. So okay. So here in this diagram you saw that the magnitude at bus 3, this is 1.015, right? Now this must be having some complex real term plus any imaginary term, right? This is what we got after calculating. So V3 after first iteration. So I mean, if you do this, I mean, if you find out what is the magnitude of this, I mean, take the square root, square of this and take the root, you would be finding that, I mean, clearly it is less than 1, right? It would be coming something around 0.96 something. You may do that. So there is something wrong. I mean, immediately you will see that there is something wrong with this thing. So I mean, the problem is that there is some, I mean, issue with the real term of this bus 3, which is 0.9557. So we have to find out what is the real part of this bus 3, I mean, voltage of bus 3. Therefore, we know what is the magnitude, which is 1.015, and we take the square root of that. I mean, just the Pythagoras theorem, right? Hypotenuse square minus your perpendicular square. It comes out to be 1.003 per unit, and therefore, um, your this thing, I mean, voltage at bus 3 after first iteration comes out to be this. So you have to replace this with this, and so they have told us to find out what is the bus voltage angle, right? So basically tan inverse of this minus this, and also with the negative sign. So it comes out to be 0.8 minus 0.895 degrees. I mean 8.95 degrees, sorry, which comes out to be your what, option number C, I guess. Yeah, it is the option number C. So this was problem number 6. Uh, if you don't have any questions, I will proceed to the next problem. So these are, I mean, uh, what to say, very calculation intensive problems, and you have to be very careful while, you know, doing this kind of complex multiplications, divisions, additions, and all. Because any mistake, any change in symbol that you may not notice may lead to a wrong answer. Okay. So now they have told us, so same again the same question, so that is why I took question number 5, 6 and 7 together. So they have again here told, so the total question is same, but again they have told ki using Gauss-Seidel method, find out the active power loss in the line 2 3 after first iteration, which is between bus 2 and bus 3, this line. So your I mean I23 after first iteration would be what? It is very simple. So V2 after first iteration. So I have forgotten to put this one here as a superscript. I will make the corrections before I upload the this PDF file. So this would be V2 minus V3 into Y23, right? So you do this calculation, you get I23 to be 0.525 plus J 0.541 per unit. Now, to find out what is the power loss, just forget active right now for the time being, just concentrate on this power loss. To find out what is the power loss, you have to find out the apparent power at this, and what is the, I mean, what is the apparent power at this bus and this bus, right? So I mean apparent power. So from bus 2 to 3 would be what? V2 after first iteration into I23. Okay, I23 star, because apparent power is V into I star. I mean the I conjugate, right? So I23 we found out it is this thing. So you do this and you see that this plus I have changed. So I did a mistake here. I'm sorry. I'll correct this. So this would be minus. Okay. So after doing this, it comes out to be this value. Okay. And for now, this is for bus 2. Again for bus 3, this would be what? Your V3 into I32 star. So I mean I32 and I23, the magnitude are same, but the notations are different, right? Because this is 32 and 23. It is not like your admittance, right? Y23 and Y32, they are same, because these are basically admittances, but these are current. These things are current, so they have a direction. When I say 2 to 3, it means that current is flowing from bus 2 to 3, and when I say it is 3 to, it means that the bus current is flowing from 3 to 2. Therefore I32 would be simple, it would be minus I23. So when you do this, it is very simple, just reverse the symbol, and you finally you take this conjugate of it. So here you can clearly see this minus I have changed it to plus. Therefore, when you do this, it comes out to be this value. Be very careful with the symbol. I mean, with the this plus and minus, because here you can see. I mean, I did a mistake while writing here, but I mean, in my rough, I did the right thing, but while copying on this thing, I forgot to change this. Anyways, so this is the main thing. So okay. Uh, Yeah, so I have written, I mean, there is a repetition of this, sorry. So this S23, I have again written it here. I will erase this. So here you can see that I have changed this minus, right? Because this was conjugate and this plus has been changed to minus. It comes out to be this. Now loss would be what? The basically, I mean, from your basic concept, it would be the total apparent power at this due to current flowing between 2 to 3 minus the current flowing, I mean the apparent power at this bus due to current flowing from 3 to 2. So that is why we have taken a plus of it. So here you may be confused a bit. Why this plus? This would be basically minus, right? But if you see, your I32 is already minus of I23, right? So that is why this plus is already been taken care of while you are doing this small operation. I minus I32 is minus of I23. The problems are solved. Now when you do this, it comes out to be 0.0142 plus J 0.1135. And in the question, they have told us to find out the active power loss, right? So we have to only consider the real part. So this is in per unit, and you have to multiply with 100, which is your base. So this is 100 MVA base. So it comes out to be 1.42 megawatt, which is your option number D. I hope, I mean, you may again listen to this recording and try to understand what I have said. It will be clear, I guess. Okay. So, if you don't have any questions or doubts, I will go to the next problem. I mean, you can speak up anytime because I have allowed the mic for you to speak if you have any doubt. Okay, so let us now look at question number 9. Again, question number 9 and 10, these are connected questions. So that is why I have taken this group of questions together and tried to solve. So this is another pretty lengthy problem and you have to know the formula of it. So they have told here a two bus power system shown in the figure supplies a load of 1 plus J 0.5 per unit, and the value of delta 2 is, they have found told us to find what is the value of delta 2. So this is the diagram, and immediately you can, looking at this diagram, you can construct what is the admittance matrix of this. So Z12 is what, between 1 and 2 it is J 0.1, and your Z11 is J 0.2. Therefore your Y12 would be minus J10 and Y11 would be this plus this, right? I mean Y1, okay, so this would be capital Y1, sorry. Yeah, okay, I made a mistake over here. So Z12 would be, Z11 would be what your, yeah, I made a mistake. I will rectify this. Anyways, this is correct. So your capital Y11 would be Y11 plus Y12. So your basically y small y11 would be what, 0.5, right? 1 by j2. I mistakenly wrote this as minus j10.5. Really very sorry for it. I'll correct this. So this would be minus j0.5. Therefore your capital Y11 would be what, j10 minus j10 plus minus j0.5. So it comes out to be minus j10.5. And your y12 would be what, minus of small y12 j10, and y22 would be your this thing minus y12, which is minus j10. Now they have told us what is the value of delta 2. So here for this we need to calculate what is the real power and what is the reactive power. We will get two equations and two unknowns. We will solve it, and we will get what is the voltage at that corresponding bus, and also the uh, the load angle, right, delta 2. So here, I mean, since delta 2 is the load angle at bus 2, therefore we will be looking at bus 2 itself. So yeah, so this is the formula, and mind you, this is, the notation is pi minus jqi. Okay, and I mean, if you go through the lectures, there is a formula for this. Okay, and I mean, there is a lengthy derivation. It will take a whole lot of time. That is why I haven't shown here. I have just shown the starting formula, and I have shown what is the, I mean, formula used for calculating the real power and the reactive power. So pi is this is the thing. So I means your bus voltage itself. So I mean, this is the formula you see here, and I will go through each and every term. So I, for our case, is 2, right, for at bus 2, and k would be 1. You can clearly see that the formula states that, I mean, in this summation k can vary from 1 to n, but it can't be equal to I, right? So n is 2 here, since this is a 2 bus system, and since I is 2, k can only assume a value of 1. It can't be 2. Okay. So now going to each of these terms here. So this yii, right, I means 2 here. So this is a magnitude of yii, and your theta ii. So theta means only the angle associated with it. Now here if you see y22, right, we are concentrating on bus 22, therefore you can easily say that your y22 would be what, magnitude is 10, right, and minus j means minus 90, therefore theta 22 would be minus 90 and y22 would be 10. Similarly, yik, which is I would be what, 2, and k would be what, 1, right? So this would be 2 1. Anyways, these are same, right? I mean need not be confused with that. Y21 and y12, these are same. So y12 or y21, it is what, again you look at the magnitude of your y12 or y21, right? It is what, j, magnitude is j, and your angle sorry, magnitude is 10 and your angle is I mean j, right, which means your angle is 90. Very simple. And now looking at this vi, it is at a magnitude of vi at an angle of I. I mean, since these are complex terms, you can represent every complex term like this symbol, right? This is very, I mean, initial things to remember, I mean, for every one of us. So V1, Vi is what? V1, looking at bus 1. So magnitude we don't know, it is V1. And angle we know, delta I, it is clearly written, it is 0. Therefore, theta 1 would be 0. And your at bus 2, it is what? V2. And your angle is 1, right? Sorry, your magnitude is 1 and angle we don't know, it is theta 2, which we have to determine. So you know every of these terms. Now when you place this, so here I have broken it and I have written this equation only for this system. So I mean, once you know this term, this equation becomes really very simple. So v2 squared, magnitude of it, it is 1 only. Y22 is 10 and cos of 90 degree, which is 0. Your y12 or 21, it is 10. Your v2 is 1, v1 we don't know, and theta 21 we saw it is 90. Theta 1, you can clearly see theta 1, it is 0. So 0 and minus theta 2, theta sorry, delta 2. Delta 2 we don't know. Therefore, this becomes our equation number 1, right? Now here you may say that I have written a minus here, right? P2 is minus 1, but in the diagram there was no minus sign. You may ask why this minus is here. This is, I mean, this I told previously, because in load flow studies, a generator bus, the power, be it reactive power, be it apparent power, the power it is being, the generator bus is generating, it is considered to be positive, and a load bus, it is considered to be negative, right? So that is why this minus sign is here. Okay, this minus sign is here, this minus, since this is a load bus, so the power, the reactive power or the apparent power, it is negative. So that is why this minus is here. Simple. This is, hence this becomes your equation number 1, right? And now here this is your equation for qi, again this equation only, and here I at the outside there is a minus here. Now this minus comes from this pi minus jqi, right? This is, I mean, this notation we have to follow for every kind of bus, be it a generator bus, be it a load bus. So that is why this minus jqi, minus wala term, is written over here. So, and again this minus 0.5, because this is a load bus, right? So that is why, I mean, this is how these two minus symbols have come. Okay, so this, anyways, this minus minus gets cancelled, and when you do this, this is your finally second equation. So they have finally told us to determine what is the load angle at the bus number 2. Okay, I mean load angle, it is clear that it is the load bus itself. So tan delta 2, it is minus 10.5. So delta 2 is what? Minus 174.56. Okay, so it comes out to be your, I mean, you have to add with this plus 180, right? So it comes out to be minus 5.44, which is your option number A. So this was, I mean, this was also, I mean, a pretty lengthy kind of a problem, and you have to again take care of a lot of things. Why this minus is coming? Why again in a reactive power? Why this minus is here? Again, why this minus is coming? All of these things you have to take care while solving the problem. And if you do everything correctly, hopefully we'll get to the right answer. And I mean, these load flow problems, especially this Newton-Raphson method, then your Gauss-Seidel method, these are pretty lengthy problems. And if I mean, you see that they have only told us to find out. I mean, in the previous problems 5, 6, 7, you saw that they told us to determine the bus voltage after first iteration. So that was only taking a lot of, I mean, pages, lot of time, lot of intensive calculation. So if they accidentally tell us to find out after second or third, it will take a hell of a time. So that is why, I mean, this type of lengthy calculations are all done by the computer itself, right? and I mean more the number of buses, more complex it becomes. So you can easily, I mean, understand how much of memory it consumes, this kind of problems. And these are really very important, I mean these are really very important part or a chapter of power system, because we have to determine what is the bus voltage, what is the power being consumed or generated at a bus, because if there is any kind of fault, I mean, in the transmission line or at the generator side or at the load side or at the transformer. So, I mean, determining what is the load, I mean, fault current, or how much impedance we need to, add to reduce the current during fault. All of these are calculated using, I mean, all of these terms are help us to be calculated, right? So, yeah, that is why these load flow studies are really very important. Okay, so having done this, let us now go to problem number 10. So this is a really very one-liner problem, and this is connected to this. So they have told same problem itself. They have told us what is the this voltage, right? V1. Okay. So you can use any of these equations. So you know what is the value of delta 2, right? We had these two unknowns, V1 and delta 2, and we had these two equations. We solved for delta 2, and you can use any of these two equations to calculate what is the value of V1. When you do it, it comes out to be 1.05 per unit, which is your option number C. Okay. Now I will come to this problem later. Now let us first look at question number 3 and 4. Okay. Yeah. So, guys, if you have any problem, you can speak up. And uh, you can unmute and speak. Okay. So now here, this is a very simple problem they have asked. So in load flow studies of power system, what are the quantities specified at a voltage control bus? So voltage control bus, right? So your option would be very straightforward. What are the quantities specified? What these are not what are the quantities to be determined. Then it would be something different. So your option is right answer is voltage and magnitude, right? Because your generator bus, the voltage and the I mean the active power, sorry, the voltage magnitude and the active power, these are the two things specified, and your reactive power and the phase angle of the bus voltage, these are to be found out, right? And this is very opposite to that of the load bus, where we have the real and the reactive power components which are specified, and your you need to determine the magnitude of voltage and the phase angle. These are, I mean, these two terms are to be determined for load bus. So again, your voltage control bus is also referred to as generator bus, and it is written as PV bus, and your load bus, it is written as your PQ bus. So these are the two, I mean, notations used. Now this was very simple problem. So now let us come to an interesting problem. This is pretty easy problem provided you know the things. Okay. So here, problem number 4, they have told that a power system consists of 350 buses, out of which 15 are connected with generators. So I have written it here. So there are total of 350 buses, 15 are connected with generator. Therefore, generator bus equal to 15. Now 20 bus are the one with control reactive power support. So therefore, your PV bus becomes you're 20. Okay, I will come to this. And one with fixed shunt capacitors, it comes out to be 20. They have written it 20. So it is proposed to perform a load flow analysis using Newton-Raphson method, and they have asked us to find out what is the size of the Jacobian matrix. So I mean, for Newton-Raphson method, you need to determine a Jacobian matrix, and every matrix has a order, right? 3 cross 3 or 4 cross 4 or whatever it is. So here, we need to find out what is the size, right? So here we know what is the PV, I mean generator bus, and what is the which is 15, and again how many are I mean, the ones with controlled reactive power support is also 20, which is 20 and shunt capacitors. Therefore, PQ bus, I mean, what are the total number of load buses? It would be 350 minus 15 minus 20 minus 20, okay, which is 295. Now, I mean, these are some of the terms which you should remember while you are solving this kind of problem. And and I mean, so here you can see that I have written, I mean, these are some of the, what should I say? I mean, these are to be considered. Okay. So they have told us that there are 20 buses with fixed, which are fixed with shunt capacitors. So buses with shunt capacitors are also to be treated as load bus or PQ bus. And your reactive power, I mean, buses are also treated as PV buses. So here there it was mentioned that 20 buses are the one. Okay, sorry. 20 buses are the ones with control reactive power support. So there are 20 buses which provide or absorb reactive power. So these kind of buses are to be treated as PV buses. So that is why I had written this PV bus. So I mean these are both the same, right? So therefore, your total PQ bus becomes what? 295. We calculated here 295 plus 20. Okay. So this comes out to be 315. And your total PV bus would be what? Generator bus we saw it is 15. It was clearly given, and we saw that the buses with reactive power support are also to be treated as PV bus. So it comes out to be 15 plus 20, and this minus one is there, so we know there is a always a bus considered as reference bus or slack bus, and this slack bus is considered to be, I mean, this is taken, so that is why these are, I mean, this one is there and we need to subtract this because this is a reference bus and we do not take this into calculation, I mean, for calculating. So this comes out to be 34. Therefore, the size of the Jacobian matrix, so this is the fixed formula, twice into PQ load bus, which is your option number B. So yeah, I hope this was clear. Pretty simple problem provided you know all of these stuff. Okay. Yeah. So now let us go to problem number 8. Here they have told key, the per unit power output of a salient pole generator which is connected to an infinite bus is given by this expression, right? P equals to sine 2 delta plus 0.95 sine delta, where delta is the load angle. Newton-Raphson method is used to calculate the value of delta for P equals to 1.40. If the initial case is 30 degrees, then its value is, I mean, yeah, so, I mean, after the first correction, they are asking, okay, I mean, if they haven't told anything, you have to assume that you may ask how many correction do I do? That delta x wala term that you have to add every time in Newton-Raphson method, how many times you may do? So, I mean, as per, okay, so they have only also told at the end of first iteration, yeah, okay. So, you have to add the delta x wala term only once because they have told to find out after the first iteration. So here they have told for p equals to 0.140, and this becomes your p assumption or whatever you may call it. So I have written it as p assumption, a double s. So it comes out to be 1.4 per unit, and your p calculated becomes this. So they have told the value of delta, which is your 30 degrees, it comes out to be 1.341. Now your correction factor delta p becomes the difference between this and it becomes 0.059 per unit, and the convention is always this, so assumption minus calculation. And this is a formula for this, so delta p equals to dp d delta into the delta, I mean del delta. So your dp d delta, you have to take the first differentiation of it, and you have to replace the value of delta here, which comes out to be 1.823. So when you substitute everything here, your this thing, it comes out to be 0.0324 radian, and you multiply this with 180 by pi, it comes out to be 1.855 degrees. Therefore, I mean, the after first correction, your delta would become initial plus that correction factor, right? And it is 31.855, which is your option number D. So yeah, I mean, Newton-Raphson method, what we do is that we try to find out the most, I mean, for every, be it Newton-Raphson or be it Gauss-Seidel, we try to find out the nearest, I mean, most accurate bus voltage, and for that we assume an initial value and try to get close to that, right? So this is the small calculation of it. So yeah. This was problem number 8. Pretty simple problem, provided you know how Newton-Raphson method works for low flow studies. Okay. Now, yeah, okay. So let us now look at the last problem. So question number 4. They have told a 13 bus power system consists of 5 generator buses indexed as G1 to G5 and 8 load buses indexed from L1 to L8. So directly, I mean, you can say that for each of these studies, we have to consider one slack bus, and it is to be considered from the generator bus itself, right, or the PV bus. Therefore, the PV bus becomes 4, right? So, okay, so they have told that the G4 is considered as slack bus, so therefore you have to subtract it. Now, they have told that the load buses are voltage L2, L3, and L5. These are voltage controlled buses. Okay, so immediately you can see that these L2 and L3 and L5, these are to be considered as PV bus or voltage controlled bus. Okay, so again here the next statement, they say that the generator at buses G2 and G5, they cannot supply the required reactive power, and hence it is operating at their maximum reactive limit. When this kind of statement is made, you have to consider that since this G2 and G5, they cannot supply the required VAR demand, so they have to be converted to the PQ bus. They have to be treated as load bus itself. So this is the convention. Therefore, the number of load PV bus would be, initially it was 4, and now you have to subtract it to 2. So this 2 goes to the load bus, right? And your initially the load bus was 8. So this becomes 8 plus 2 goes to 10. Now they are saying that this L2, L3, and L5, these are to be taken as voltage control bus or PV bus. So these 3 buses, they cannot be there for PQ bus, they have to convert it to PV bus. Therefore, you have to subtract 3 from 10 here, 7, and you have to add the 3 to this 2, to this new PV bus. So it becomes 5. Therefore, your required Jacobian matrix would be what? I mean, it would be what, so we saw here, it is always 2 into load bus plus PV bus, right? So it becomes 7 into 2 plus 5. Therefore your matrix order would be 19 plus 19. So it is option number A. Yeah, so this was problem number 4, and this was the last problem of today. So I will be uploading this video by tonight itself, and I will be uploading this file also by tomorrow morning. Uh, yeah, so this was all for today. If you have any questions, any doubts, you can ask. Otherwise, you can leave. The session is over.
Can you upload this PDF file today or now because I'm just planning to take a printout in next 15-20 minutes.
Okay, okay, okay,
Only this
fine.
PDF file, video file. Okay, that is a different thing. Just PDF. This one.
Okay, okay, fine. Yeah, I'll upload it maybe in the next 5 minutes.
Yeah, there was another parallel session going on. I don't know whether you know
Yeah,
it.
there was a live session. Yeah.
Yes, yes. So I was many people were attending that session. So I think that is the reason why the participants were less in this session. Both happened at the same time.
I mean,
That is
many
also 7 o'clock
students.
to 8 o'clock.
Yeah, it clashed. I mean, many students joined here and they left. I mean, immediately. Some of them
Okay,
stayed back. A lot of people joined. They left immediately.
okay, okay.
Yeah. Okay, fine. I will
Yeah,
upload this. And if you have any doubt, you can write to me in the comment section of the YouTube. Okay, video. I will try to answer.
okay, okay. Yeah, yes, that is fine.
Okay. Yeah.
Yeah, thank you.
Okay. So
Shobhik.
yeah, we'll meet next.
Yeah,
Bye.
yes. Okay, thank you. Bye.